In this video, I'll introduce the concept of distance in graphs. We'll look at an example of this and compute some distances. And finally, we'll talk about some properties of distance. So for distance in graph, we're assuming we have a connected graph. That's sort of our base assumption for distance, that the graph be connected. And remember what it means for a graph to be connected is that between any two vertices there exists some path between them. Remember, a path is a walk that doesn't repeat any vertices. So between any two vertices there's some path between them. And indeed, there might be many different paths between the two vertices. So what we can do is we can pluck out the shortest path. So of all the UV paths, we look at the very shortest path between U and V. And the length of that path is what we call the distance. So the distance between two vertices is the length of a shortest UV path between those two vertices. And then another term that comes along with this is geodesic. So a path that actually achieves the minimum length, so a path whose length is the distance between the two vertices, is called a UV geodesic. So let's take a look at distance in graphs. Let's actually compute some distances. So here I have this graph of order 10, and let's compute the distance from V1 to some other vertices. So how about, let's look at, how about V1 to V7? So I want to think about all the different paths that I can take to get from V1 to V7 and come up with the shortest one. So I guess the first thing to notice here is V1 and V7 are not adjacent to each other. So the shortest length is greater than 1. Next, notice that any neighbor of V1, in particular V2 and V5, is not adjacent to V7. So the distance from V1 to V7 is strictly greater than 2 as well. However, I can find a path of length 3. So for instance, V1 to V2 to V6 to V7 is a V1, V7 path of length 3. So let me write that down. V1 to V2 to V6 to V7 is a V1, V7 path of length 3. And the argument I was just describing there, right? There's no path of length 1 because they're not adjacent. There's no path of length 2 because any neighbor of V1 isn't adjacent to V7. And so the shortest path must be length 3. So this is a V1, V7 geodesic. And the distance in G between V1 and V7 is 3. So this is the length of a shortest path is the distance. Right, so you might notice that for anything adjacent to V1, so V2 and V5, that it's really easy to find a shortest path because they're adjacent. In particular, I'll point out V1, V7, that path is a V1, V7 path of length 1, and certainly we can't do any better than that. And so the distance between V1, not V7, V1, what did I want to say there? V1, V2. V2 path of length 1. So the distance is V1, V2 is 1. So for any two adjacent vertices, if UV is an edge of any graph, then the distance between U and V is equal to 1. So the distance is 1 if and only if the two vertices are adjacent, right? And if the distance is 1, then certainly there's an edge there. So that's an if and only if. One curiosity here is, what's the distance between a vertex and itself? So what's the distance between, say, U1 and U1? Well, there's only one path. There's only one path from V1 to itself, and that's the trivial path. So that is the path that contains no edges. So the path, I'll say the trivial path, just V1, is a V1 path of length. How many edges? Well, it's trivial, so there's no edges, of length 0. And so the distance between U1 and itself is 0. In general, the distance between any vertex and itself is 0. Let's compute a couple other distances here. How about V1, V8? So I want to think about all the different paths from V1 to V8, how I can do that. I mean, I could come over here and go around there and go to V8. That one probably won't be the shortest. So let's see. Clearly, they're not adjacent, and so the distance is greater than 1. Also, the neighborhood of V1, no vertex in the neighborhood of V1 is adjacent to V8, and so the length is strictly greater than 2. So can I get there in 3 steps? 1, 2, 3. No. 1, 2, 3. And I can try sort of all the different possibilities here and see that there's no paths of length 3 between V1 and V8. However, there is a path of length 4 between V1 and V8. V1 to V2, V2 to V3, V3 to V4, and V4 to V8 is one such example. Another example would be V1 to V5, V5 to V6, V6 to V7, V7 to V8. 1, 2, 3, 4. So there's 2 different V1, V8 geodesics. And so the distance between V1 and V8 is 4. Distance in G from V1 to V8 is equal to 4. And we gave an example of a couple different geodesics. So in general, this is the process that you go through, is you look at all the different ways I can get from one vertex to the other and find the very shortest way. The length of that path is the distance. So this is, distance in graphs. It gives us a measure of how close the 2 vertices are to each other in terms of the structural properties of the graph. So rather than actual like physical distance, I more care about how many edges do I need to take to get from one vertex to the other, right? And this coincides with how we think about graphs. We don't care how we draw them so long as the edges are preserved, right? And so for distance, we just count the number of edges between the 2 vertices. That is, we count the number of edges in a shortest path between 2 vertices. And that's distance. So there's some properties that come along with distance. In particular, a graph together with the distance function is a metric space. Now it's not super important that you know it's a metric space. If you've heard this term before, that's great. But I'll just list the properties of a metric space. So the distance between 2 vertices u and v is greater than or equal to 0 for all uv in the vertex set of the graph. In particular, we can't have negative distances, right? Our definition of distance, that wouldn't make sense. The distance from u to v is 0 if and only if u is equal to v. So this is an important property of a metric space to have. Right. Distance being 0 means there has to be a walk of length 0 between u and v. Well, that's a trivial walk, and so u has to equal v. And as well, u equal v, then we have the trivial walk between them. So that's an if and only if. We have the symmetric property, distance from u to v equals distance from v to u for all uv in the vertex set. Right, and why is this? Well, a shortest uv, I could say rather a uv geodesic, is also a vu geodesic if I just reverse the order of the path. And therefore, yeah, the distance from u to v is the same as the distance from v to u. Now, this is an important one because instead of saying a distance from u to v, Well, we can just talk about the distance between two vertices rather than from one to the other. Since it doesn't matter which one comes first, we can just say the distance between two vertices, and there's no loss in generality there. And lastly, here's another important one. This is the triangle inequality, the distance from U to W. If I pick any other vertex, that this will be less than the distance from U to V plus the distance from V to W. And this is for all U, V, and W in the vertex set of G. So this is the triangle inequality. And how would we go about proving this? Right, the book doesn't prove this for us, but we can think about it, right? So I look at a UW geodesic, and I want to say that that length is less than or equal to the sum of the distance between U and V and W. Well, if I take a UV geodesic and a VW geodesic, and I stick those two paths together, I concatenate them, then what I'll obtain is a path between U and W. It might not be a UW geodesic just because UV was and VW was, but it's certainly a path from U to W. So the distance from U to W, it being the shortest UW path, has to be less than or equal to what I just did there to get my UW path. And so certainly this triangle inequality holds. So right, as I said, this tells us that graphs together with this distance function give us a metric space. And we can talk about, instead of distance from one vertex to another, just distance between two vertices. All right, in the next video, we're going to use this concept of distance to prove a really nice result for bipartite graphs. In particular, we'll finally be able to give a characterization for bipartite graphs using distance. All right, see you there.